All right, let's talk about something that shows up on physics exams and kind of scares people, the Hall effect. But here's the thing, I promise you, by the time we're done here, you're going to see it's actually super logical. So let's just jump right in. You know that feeling, right? You're in an exam, you turn the page, and bam, there's this huge, scary-looking question. Your stomach just drops. But honestly, a lot of the time, those questions are just testing one simple idea. And if you get that idea, they're basically free points. Well, the Hall effect is totally one of those questions. Seriously, once you get the logic, and you only have to get it once, you can handle anything they throw at you. So let's break it down together piece by piece and turn this thing from a headache into your secret weapon for that exam. Okay, so where do we start? With the definition, of course. You've got to nail this part. Getting the definition right from the get-go is huge. We're talking 2, maybe 3 easy marks right there. So what exactly is the Hall effect? Let's boil it down. It's what happens when you get a voltage sideways across a conductor. The catch? You need 2 things happening at the same time, a current flowing through it and a magnetic field cutting across it at a right angle. Current one way, magnetic field another way, boom, you get this transverse voltage. And that sideways voltage that just kind of appears out of nowhere, well, it has a name, and you guessed it, it's called the Hall voltage. That's the thing we can actually measure. It's the final result of this whole process. Yep, simple as that. Now, let's really picture this, because it's all about 3 dimensions. Think of a flat strip of metal. Okay, first we've got current flowing down its length. Let's call that the x direction. Got it? Next, we bring in a magnetic field pointing straight up through the strip. That's our z direction. So what happens? A voltage shows up across the width of the strip in the y direction. See? It's this perfect x-y-z relationship that makes the whole thing work. Okay, so we know what happens. But the big question is, why? Why does this voltage just show up? Well, the secret, the key that unlocks this entire puzzle, is a little something called the Lorentz force. Now this right here, this is the golden sentence for your exam. If you remember one thing about the why, make it this. The Hall effect isn't some kind of weird magic. It happens for one simple reason. The Lorentz force is physically pushing the little charge carriers, the electrons, as they move. And here's the formula that makes it all happen. It looks a little intense, but it's not so bad. The force, F, depends on the charge, Q, how fast it's moving, V, and the magnetic field, B. The important part is that little X symbol, the cross product. All that really means is if your velocity and magnetic field are on 2 different axes, the force they create will be on the 3rd axis, totally perpendicular to both. That's what gives us that sideways push. So let's put it all together. You have these electrons flowing, right? The current. Then this Lorentz force comes along and literally shoves them all over to one side of the conductor. It's like a traffic jam of electrons on one edge. So now you have a bunch of negative charge on one side, and the other side is left all positive. And what happens when you separate positive and negative charges? You get a potential difference. You get a voltage. And that, my friends, is the Hall voltage. All right, theory's cool, but let's get into the numbers. How do we actually measure and quantify this effect? We use something called the Hall coefficient, which we write as R with a little h. Think of it as a number that neatly connects the electric field we get to the current and magnetic field we put in. And this simple little formula, this is your best friend for any math problems they give you. The Hall coefficient, RH, is just 1 divided by n times q. Now, n is just how many charge carriers are packed into the material, and q is the charge of each one. But what's really cool is what this formula lets us do. It's like having X-ray vision to see inside a material and count the electrons. How awesome is that? So at this point, you might be thinking, okay, this is some neat physics, but so what? Why does this even matter? Well, it turns out the Hall effect is way more than just a weird theory. It's an incredibly powerful tool that helps us understand the fundamental properties of materials. Just by measuring that Hall voltage, we can learn so much. We can figure out if the charges moving are positive or negative. We can calculate the exact density of those charge carriers. We can even figure out how easily they move around. And for semiconductors, we can tell if it's an N-type or a P-type. I mean, that is just a massive amount of information from one simple measurement. And because it's so useful, you see it in the real world all over the place. Those things are called Hall sensors. They're in your car's ABS system, taking your wheel speed. They're probably in your phone, helping the compass work. They're used in labs to measure magnetic fields with crazy precision. And hey, quick tip for the exam, listing a few applications is always an easy way to grab some extra points. Okay, let's wrap this up and put a bow on it. To make sure you walk into that exam feeling totally confident, here's your 5-step game plan for any Hall effect question. So the second you see Hall effect on the test paper, just run through this checklist in your head. 1, nail the definition. 2, describe the setup, the XYZ thing. 3, explain the principle. Don't forget to say Lorentz force. 4, write down the Hall coefficient formula. And 5, list a couple of real-world applications. If you do that, you've covered everything. You can't go wrong. Seriously, just follow that flow. If you do, the Hall effect goes from being this complicated, scary topic to one of the most straightforward chapters you'll study. It becomes predictable, and that's exactly what you want in an exam. So, how do you feel after breaking it all down like this? That big, scary topic doesn't seem so bad now, does it? You've got the logic, you've got the structure. You are absolutely ready to tackle any Hall effect question they can come up with.